Well, good evening, everyone, and welcome to LSU Science Cafe. I'm Steve Beck with the Office of Research and Economic Development, and we're excited to bring you tonight's program featuring research by LSU Department of Civil and Environmental Engineering Associate Professor Ali Musaad Ali. As we saw from Hurricane Ida as it made landfall in Louisiana, wind and the damage it can cause should not be underestimated. Dr. Ali will talk about this and the powerful one-of-a-kind wind laboratory he has built at LSU that can produce up to Category 4 hurricane winds to test wind resistance for homes, commercial buildings, and energy infrastructure and improve resilience. Live closed captioning for this event is available. Please click on the live transcript button at the bottom of your screen. Despite our physical distance, our goal is to continue to build a strong, informed community by providing access to reliable information, new ideas, and cutting-edge research, scholarship, and creativity from faculty experts and researchers in fields across the university. Tonight's event is brought to you in a new partnership with local public radio station WRKF 89.3 FM. And to introduce this new activity, this new endeavor, I'd like to introduce our friend and collaborator and WRKF membership manager, Gwen Pelagi. Gwen?
Thank you, Steve. We are so thrilled to be collaborating on LSU Science Cafe, and WRKF, which you can find at 89.3 FM, is your source for local news and programs like Science Friday, the TED Radio Hour, Hidden Brain. And now you can also watch LSU Science Cafe on WRKF's Facebook page, and we're thrilled about that. You can learn more about your public radio station at WRKF.org. And tonight, WRKF will be giving away one stainless steel NPR beverage tumbler to one lucky audience member. And to enter the drawing, just click on the link in the chat box and fill out the Google form with your contact information.
Thanks, Gwen. We are so excited about this new partnership and the future that it holds for both our organizations. Thank you, Gwen, for everything that you've done for this, and thank you to everybody at WRKF. Please be aware that this online event is being recorded and it will be available with a transcription from the LSU Research website within the next few days. And now, without further ado, I'd like to introduce tonight's speaker. Dr. Ali Musaad Ali is an associate professor at LSU. His research aims at creating fundamental knowledge, wind engineering, dynamics, and control to build more resilient economic and recoverable energy and coastal infrastructure that can enhance safety and reduce the huge cost of rebuilding after windstorms and earthquakes. Ali established the LSU Windstorm Impact Science and Engineering Research and Education Program at wise.lsu.edu. His research enables advanced wind testing by meeting the challenges of yielding loads that mimic full-scale true physics. His research advanced the implementation of smart dampers in super tall structures and led to a novel probabilistic theory that enables analytical modeling of the semi-active damping technology. Ali holds a PhD from Polytechnic University of Milan in Italy and has worked as a research fellow at the West University in Canada and a research associate at the International Hurricane Research Center in Miami. After the presentation, we'll have a moderated quiz, question and answer session. To participate, please use the Q&A button to enter your question. We will be monitoring that section and relaying them to our panelists. And now, I'll turn it over to Dr. Ali Musaad Ali. Ali?
Hello? Yes? Can you hear me?
Absolutely. Go ahead.
Thank you very much, Dr. Beck, for the very nice introduction. Thank you, everyone, for attending and being with us today. It's a great honor for me to give a short talk about the research that we do here. Next, please. So for any research, there is a question, and the question comes from the problems that hurricanes bring to the economy, to the built environment, and almost to everything on Earth. So if we look at the here is a motivation, which is the economic losses. Over the years between 1980 to 2019, hurricanes brought about $1.75 trillion of losses. Next, please. And usually the losses are in terms of flood, wind damage, and other things. So recently, Hurricane Ida brought damage to Louisiana, and that was in a form of flood and damage to the infrastructure. So absolutely, to avoid damage to these buildings, we need to have a good understanding about how they interact with wind to avoid wind damage. So if we were to protect building against flood, we could do something like elevated homes. However, even elevated homes can be subject to damage. As we can see, due to Hurricane Laura, again in Louisiana, elevated homes were also subject to damage. Not only residential homes and high-rise buildings, but also energy infrastructure, the green energy infrastructure, like solar panels. The bottom right corner here, we see damage came to a solar farm in Puerto Rico, and that was after Hurricane Maria. Next, please. Same story with Hurricane Irma. Next, please. And Hurricane Michael. To Tyndall Air Force, damaged residential buildings, and other types of infrastructure. Next, please. This has been a history. It's not just recently. Of course, recently, climate change, there is an increase in the intensity and the number of hurricanes and windstorms. But since 1992, when Hurricane Andrew hit Florida, and there was a development over the years for stronger building codes and standards, but we still can see the damage up to date. Next, please. So if we think of residential home, low-rise buildings, mostly the damage will start from the roof. And why is that? Next, please. It is because these type of infrastructure are bluff bodies compared to streamlined shapes, like, for example, the airplane wing. And this will lead to flow separation, and the flow separation will cause uplift forces that cause the damage to building. And usually the damage starts from the roof. But the lower bottom one, this is unusual case where there was base isolation to protect the building against earthquake. So it made the whole thing softer, but this is not very common. Next, please. Next slide. So as I mentioned, that is because being bluff bodies, the flow will separate and create uplift forces. If you click on the lower left corner, the cube down there, this is visualization of what is happening. So in fluid mechanics, this is a flow separation that creates negative pressures. It's you think of a giant vacuum cleaner or something that uplifts the whole roof. Next, please. So where is wind engineering from this? Well, wind engineering will deal with the interactions between the wind in the atmospheric boundary layer and almost everything on Earth. Next, please. So if we were to understand that to build a more resilient infrastructure, we need first to model the wind, and this can be done by modeling the wind in something like wind tunnels or open jet, or even computationally in computational fluid dynamics. So there is interaction with the built environment, which can be anything on the surface of the Earth. Why we do that? Because there is damage and there is inconvenience. Inconvenience like the flow around high-rise buildings, this can cause discomfort. But there are also benefits. Wind is not always destructive. Moderate wind can be used to generate electricity, wind turbines, pollution dispersion, and also it is useful for natural ventilation and things like the heat island in the cities. Next, please. So in order to do that, we rely, or the researchers have been relying on wind tunnels since about 1960 up to now. And wind tunnels is kind of, we have a test section, wall bounded, and we are creating flow of air in it. And then we put roughness elements in it to try to produce the turbulence, because wind at full scale has unique type of turbulence. Next, please. So as we can see here, this is what is inside a wind tunnel. We have a building scaled, and the scale here is the geometric scale, 1 to 100, and being tested in a wind tunnel, we can see things like spire, roughness element, and these are to create turbulence. And this has been very useful over the years. Thanks to wind tunnels, we have seen lots of high-rise buildings, towers successfully designed. But next, please. The issue became more evident when we want to test things that are smaller size in the atmospheric boundary layer, things like green energy infrastructure, even residential homes. So the number before was 1 to 100, and this one of the largest wind tunnels. 1 to 100 scale, it means if the building is 200 meters height at full scale, it becomes 2 meters in the lab. But what if we use the same scale for something like a solar panel, which is 100 by 200-300 meters or something around that, then the size becomes really small. It becomes like 1 centimeter by 2-3 centimeters, and then it becomes very challenging to test it by the traditional wind tunnel. And I have to do that because the flow in this type of wind lab is scaled in a way that the integral length scale of turbulence is 1 to 100, 1 to 400. So huge uncertainty in this case of testing, and the turbulence the physics are not the same. Add to that the lack of the Reynolds number are not matching with what we have at full scale. So this is one of the biggest challenges that we have with wind tunnel testing. So next, please. So with OpenJet, we can overcome these issues by testing a higher Reynolds number and reproducing larger scale turbulence. Next, please. So this is the OpenJet facility, and it is this can produce a flow of each engine here is about 800 horsepower. So the flow we can produce is really can be at high speed. Next, please. But also because of the lack of we don't have walls here that is immediately surrounding the high-speed flow. So the walls are located at a further distance, and that really gives us a chance to create more turbulence than what we have in what I call wall-bounded wind tunnels. So the concept is explained here, and we have a test model should be located at certain distance and with certain size. And to show an example of this, next, please. So it was the cladding for high-rise building, a study motivated by the failure of the glass and the cladding here. For example, windows of the Capital One tower after Hurricane Laura in Lake Charles, 2020. So we wanted to understand why is this happening. So before that, we saw that wind tunnels are good at predicting pressures or even high-rise building, but it seems like it's not. There is something here. There is still even a gap with high-rise buildings. So next, please. So we brought this high-rise building to lab with a scale 1 to 50, and we tested, as we can see here, this is the building, and from inside we have about 256 pressure taps, and these are connected to high frequency pressure transducers to acquire pressures on the surface. Next, please. And here is what we got. If we look at these are peak loads. So subfigure A is the windward facing side of the building. And as we can see, we got pressure in the order of 2.5. These are pressure coefficients. But in the corresponding wind tunnel, they are lower. They are even much lower on the side wall. We got a coefficient in the order of -4. I'm talking here about the magnitude or the absolute value. But in the wind tunnel, around the same higher location, we have things around 2.3, 2.2. So it's almost like twice they are. So we have higher loads compared to what was predicted in a wind tunnel. Next, please. And this is matches with the facts that we have. So the blue dots here, these are average of 6 reputable international wind tunnels. They got pressure coefficients here, and then the full scale significantly deviating from what is in the wind tunnel. So it is almost like twice or 0.5, 0.7 what they get. So that in nature or at full scale, the loads are much higher than what is in classical wall-bounded wind tunnels. However, in the open jet, we are able to get something that matches more like what we have at full scale. Next, please. So this is also another case study where these are trees where for a project in Italy, they call it like a vertical forest, where we have on the balconies trees like this, and we wanted to make sure that they will be safe and secure under wind. So we tested things at full scale from the tree itself without any modeling, because if we were to do this in a wall-bounded wind tunnel, we need to scale it down, and then the tree will not be from the true material. So we were able to predict the physics at full scale, which is trees under high speed, they tend to bend and the shape tend to be reduced, leading to lower forces as if we were to predict it in a wall-bounded wind tunnel. Of course, the tree has to be healthy here in order to change shape over with the increase with the wind speed. Next, please. We did also vibration mitigation in traffic lighting support structures, and these type of structure are also subject to damage due to wind. Next, please. And as we can see here, we tuned the lighting boxes to act like tune mass dampers or energy absorbers to reduce vibration, and that worked effectively. Next, please. Also for wind turbines, they could be subject to damage due to wind. If they are offshore, then it is wave. And if it is a seismic zone, then they are also subject to damage due to earthquake. Next, please. And here is we applied, this is the kind of damage that we have. Of course, what happened to the tower, this can be prevented by vibration control. Next, please. So we modeled wind turbine under the action of wind, wave, and earthquake, and we proposed semi-active control system with, and the approach worked very good. Next, please. And we can see here the red line is controlled, and the dot line is the uncontrolled. So the outer bracing and smart dampers as semi-active tune mass damper are working effectively. And we expect this not only to reduce vibration and protect the tower and the structure, but also to increase wind turbine availability, because if there is vibration, even without damage, we cannot just extract the energy. Next, please. This would show, if you click on the figure down there, yeah, it just shows the uncontrolled and controlled case. The one on the left is uncontrolled, so large amplitudes, and the one on the right is controlled with could we go to the next, please? Solar panels also are subject to damage due to wind, and this is a solar farm after Hurricane Maria in Puerto Rico. So we wanted to understand why is this happening. So we actually did here a CFD study. You see the Google, almost half of the solar farm, the panels are damaged. Extreme damage here due to wind. So next, please. So we did a CFD study looking at panels in the array, and we figured that if the original design was to be reinforced by increasing the price of this solar farm just 2%, it would have prevented damage in the order of 50% of the whole solar farm. Next, please. So this is what we are trying to do. In order to achieve a resilient economy, uninterrupted businesses, we really need to have resilient infrastructure, resilient and recoverable infrastructure. And while we are doing this, there are a lot of educational activity from K-12 to the graduate level, as well as outreach activity. Next, please. So our interest in wind engineering is always related to what is happening to building stock, low-rise, high-rise buildings, energy infrastructure, transportation infrastructure, and almost everything on Earth. How can we build them to be more resilient, sustainable, smart, and in an economic way, and reduce the consequences of failure. With this, I end my presentation, and any questions, please.
Dr. Ali, that's some really fabulous work. There's so many questions that come to mind. We have a couple already in the queue, but before we do that, I wanted to just ask you a really straightforward question. How did you become interested in wind engineering specifically? It is such a it certainly seems here in Louisiana to be a really critical area of study, but I just find it interesting how people get attracted to certain areas of discourse and research, and I think our audience would like to know that as well.
Well, that's a little difficult question, because I seem like I live with the wind. So when did that start? Maybe a long time ago. Maybe my interest, it came to my mind just after my master's degree when I did things for vibration control in buildings under earthquakes. And then the question was, is this going to work also for wind, like multi-hazard things? And I traveled to Italy, Polytechnic University of Milan, and there I found a lot of projects. Wind is just more than the dynamics for buildings and how to protect them. There are other things, bridges, low-rise buildings, and all kind of infrastructure on Earth. So I became more interested and challenged it. So there I was, my PhD was about high-rise building and vibration control. And then what is happening to low-rise buildings? They don't seem to move the same. The physics are a little different, and the way they interact with the wind, it is different. And I wanted to build on that and know more and contribute to the research. So I got an offer from Florida International University, and there we started to do things in a little different way from wind tunnels. And then I went to one of the largest wind engineering let's say, institution now. They have the WINDE at Western University, but they have history with wind engineering. It goes back to Professor Davenport, who started building things, wind tunnels and testing high-rise building. Now, wind tunnels are everywhere in the world.
Well, it's really, it certainly is fascinating and applicable to us in a time of changing climate, and certainly here the impact of wind we feel every year. It seems it's just been increasing, and in thinking about wind and hurricanes in particular, we have a question from David Trossman. Reflecting a nearly decade-old study that suggests that an array of wind turbines could buffer the impact of hurricanes that make landfall. Other than the political obstacles to deploying such arrays off the coast, is there survival under hurricane conditions the primary challenge that would need to be overcome before some kind of an approach like that could be undertaken? What are your thoughts on that?
Well, wind turbines would convert the energy to electricity, and obviously that's we got part of it. But if we run a wind turbine during a hurricane, and this is actually one of the purpose of the study I did on vibration control in wind turbines, I don't know if we can extract the energy at that time. I'm not sure. We need to look at that more, because when we have significant vibration, I need to turn the wind turbine off and put it in a parked position to protect the structure. At least
Sure.
the way it is designed now. So there is a maximum wind speed. I cannot go above it.
Right.
So, but it's interesting to look at something like that.
It certainly seems like a provocative idea, and to be honest, I haven't really, I had not heard of that study before. But then again, I'm not a wind engineer, so I think I can be forgiven on that. I did have a question on a term that you used, a Reynolds number. For those of us who are not wind engineers, what is a Reynolds number, and how does that impact the research that you're doing?
Right. So in a mathematical expression, I would say Reynolds number is rho VD over mu, which is rho is the air density times V is the velocity of the flow, and D is a dimension, which could be diameter of a structure or a length of the structure, divided by mu, which is the dynamic viscosity of the air. So this is a dimensionless number instead of, it goes back to the Buckingham theorem and how to obtain empirical expressions by doing an experiment. Let's say I want to know how the force is impacted by certain parameters, a force on a building, for example. I could say the velocity, I could say the fluid in general. I mean, it shouldn't be just wind and building. Let's say fluid in general. So the density play a role, the dynamic viscosity also, and the size of that. So they put them in a dimensionless number to make things easier, to make me run the experiments easier. But how is that in wind engineering impact the results? Well, if it is the shape is cylindrical, like a chimney, so at certain Reynolds number, I would get a certain drag force. So even when Reynolds number is a dimensionless. So what I'm talking about, the drag is the drag coefficient. So the coefficient of force is a number, all right, that when I multiply it by half rho v square and the projected area of the structure, I would get the force regardless of the speed. So this actually enables me to test things in the lab, and I can still predict the forces on a larger scale. So it was evident from the very beginning that cylindrical shape will have different drag coefficients over when I change the Reynolds number. But people have been believing for decades that buildings and structures with sharp edges, regardless of the Reynolds number, I will still get the same coefficient. And that's why they have been testing things in wind tunnels. So the Reynolds number in a wind tunnel is significantly low compared to the Reynolds number that we have in an open jet.
Okay, so
we just realized it does impact the physics. So so testing things at higher Reynolds number, even with sharp edges, is not the same as low Reynolds number.
So it's a way of aggregating a lot of different parameters into a figure that can provide a general feedback on the strength or the magnitude of the forces that are at play.
Right.
Okay.
No, it's just to make the running the experiment easier. We call them dimensionless parameters.
Sure. We have an anonymous question from someone who asks, as you may know, the federal government really determines how our infrastructures can be improved and how to pay for those improvements. If there's anyone in a governmental position listening to our presentation today, to your presentation, what key points would you want them to know about the role of engineering science to make our infrastructure more safe and sustainable for those of us living in Louisiana and elsewhere throughout the country?
Well, I would like to say that one important thing is the structural engineer rely on is the codes that point them to something called the standard to obtain loads to build things to resist wind. And this has been updated and over the years relying on the physics on wind tunnels. So what we really need to do is update this by testing the infrastructure again in something like at larger scale testing in order to update the information, because the issue is engineers are doing their job, structural engineer, right, but the code has some knowledge gaps. So that's what we really need to invest in, not just myself, but other researchers in wind engineering is really almost everything. And
go ahead.
Outcome to be documented and the standard be updated. So when the structural engineer use that, they are using recent information that.
Okay, that's really important information. And I think that planning, I mean, one of the grand challenges with infrastructure is that it takes a lot of money and a lot of time, and we have a lot of infrastructure that needs to be rebuilt to address the discoveries that we've been making in the labs. You mentioned the maximum wind speed that a wind turbine could withstand. Nanette Oliver asks us, Olivier, Nanette Olivier asks us about what that speed is. And if I could follow up on that, how do you determine that speed? And what are the important things we need to know about that?
Well, it really depends on the design of the wind turbine. Its efficiency at certain speed, you can get the maximum power you can, but if you go above that, you're not just getting the energy. Too much speed will not lead to more energy. So this is something related to the aerodynamics of the blade of the wind turbine. And add to that, at higher speed, things will start, the chances for higher vibrations are very high. And having high vibrations, think about the anatomy of wind turbine, what it has from inside. There is a generator, gearbox, things like that will not just function properly. So there is a maximum, but I'm not saying this is the end of the world. Of course, at least this is what is there in terms of wind turbine. But with research, probably researcher can push it to much higher winds.
So I guess a question that you just raised there is
Depends on the
why?
technology.
I'm sorry?
It does depend on the technology that is out there. So if I remember well, perhaps something like 25 meters per second. I'm not very sure about the number, but it's something like that. And really depends on the technology. But if there is a chance to improve the technology, we might be able to go to much higher wind speed.
So I guess the question that comes to mind with that is one that you raised. It's actually quite provocative for those of us not in engineering, that higher wind speeds do not necessarily mean more energy is being captured by the turbines. Can you, I mean, is it true? Is it simply that the systems are unable to handle the higher wind speeds and therefore can't generate it, or is there some other process at play that prevents or that leads to the situation?
Well, think about the aeroplane, right? So increasing the speed of up to Mach number, just before Mach number 1 will require more fuel, right? But if you are successful to pass that, there is a shock wave, and then you go above Mach number 1, then the need for fuel will become much less. So things are happening. This is related to the physics and the drag and the useful lift component of force, which is, remember when we talk about Reynolds number, it's in somehow similar. So okay. The forces will change.
So I want to kind of take a slight turn. We've been talking a lot about wind, but I'm from Southern California. I'm really familiar with earthquakes, and I'm really fascinated by how the work that you're doing is related to earthquakes. And I'd really like to kind of dive in for a few moments. How do you see the work that you're doing, not just affecting earthquakes as they affect wind turbines, but earthquakes as they affect other kinds of buildings and other kinds of high rise? This is a huge topic out on the West Coast, and really anywhere there's a propensity for earthquakes. And I'm, as I said, I'm most familiar with it. So any thoughts on that?
Absolutely. In fact, this is one of my current research areas, but a presentation over 10-15 minutes, I couldn't put everything. So we are already doing vibration control in buildings under earthquake. in wind at the same time, because the issue is the technology that is out there, like things like what they call it tuned mass damper. It would be ideal for vibration reduction in high-rise building under wind, but when it comes to earthquake, the performance become less, and almost it's not working for reducing accelerations in buildings. So the issue with earthquake is two things. One, it can just cause damage to the structure itself, and there is a need for damping, and that's what we do. Like, think about the suspension system of the car, right? So in order to provide comfort for the passengers, there are a lot of things there called dampers or dashboards or energy absorber. So that's what we try to do. So for low-rise building, we do something called base isolation. So you left the whole building on isolator, and this really can dissipate the energy. But base isolation might not work for wind, because wind has a static component and can push the whole building in one side. So it puts permanent drift there. So we came up with a system called bounding tuned mass damper, which is the next generation of tuned mass damper, and we got very interesting results. We are able to put just one type of damping system in a high-rise building and reduce vibration due to wind and earthquake at the same time for the first time. So such a device was not working before, but we got very interesting results. So yes, we have a lot of work on the other side on high-rise buildings with vibration control under earthquake as well.
Sure. I know that I've seen these kinds of dampers put on built-in high-rise buildings on the West Coast. I know that both in Los Angeles and San Francisco, those sorts of things are used. But it's exciting to see how those things are impacted when the characteristics of high wind are also applied to that. We have a couple of additional questions. I think these are more like along the lines of comments from James Madden, that the blades of wind turbines are more like wings on an airplane as opposed to the blades on a Western windmill used to pump water. Can you describe maybe how those differences work? And I'm assuming that they are far more as in terms of capturing energy from the wind and transferring it. Are there other things that we ought to know about those kinds of differences?
Right, absolutely. Think of the airplane wing. Over the years, there have been a lot of improvement until they came with the shape that we call it airfoil. And the whole purpose of that, it came after a lot of testing, is to maximize what you want and minimize what you don't want. How is that? So think of the airplane. We really need uplift force, right, to balance the weight of the airplane. So we look at the shape of this. And we also need to reduce the forces that we don't want, which is called drag. So to push the airplane, you need fuel to push it. So this shape came after a lot of research and study, and I believe a similar shape also is in the wind turbine, so that we reduce the drag and maximize the lift. But in that case, the lift is what causes the wind turbine to rotate. Whole thing rotate and create so it is being done in a very efficient way. But around 1970, they thought of doing it the same way they do the blade for the helicopter as well, right? But they realized some issues that because wind turbines are most of the time in the lower part of the atmospheric boundary layer, which has unique turbulence. And that caused some failure, but then again, there is a lot of improvement in the materials.
So Hampton Peel has a great question that applies directly to as a great follow-up to this. He's seen articles about wind power generators that vibrate like a musical stringed instrument vibrates instead of turning turbines. Can they withstand higher wind speeds and than the wind turbines can? What can you say about those kinds of devices?
Well, let me acknowledge that I am not exactly into the wind turbine as a device. I touched it from a vibration reduction point of view, but
Okay.
I'm aware of what is there in terms of technology. There are different ways. This is they use piezoelectric material to change the vibration to electricity. I'm aware of that, but the issue was how much power can we get with that technology? It's minimal. It's not much. It's not significant. These days, there's also what is called micro wind turbine. The smaller turbines that anyone can put it on the roof of a building. And someone told me in New Orleans during Hurricane Ida, this small wind turbine failed and caused kind of damage to the roof, and then the water came in. So we should be aware about the wind load also on something like this, because yes, it creates a significant electricity at higher wind speed, maybe at up to a certain level, but we should be careful with designing the system and where it is supported, where on the roof. And yes, there is a lot of type of technology, and I believe it is interesting to look at that. I think micro wind turbine are very important, and because they would reduce the load on the grid and provide a localized wind for each home. I would integrate that with solar panels as well. So when there is no wind, I might be able to get solar energy.
So our conversation has led to another question that I had that I wanted to explore, and that is that a lot of the things that you're studying are devices that we have identified as the future of energy, the future of clean energy in particular, whether it's wind turbines or solar farms, and the potential for damage to those devices during a hurricane or other strong wind events, tornadoes. That does seem to run counter to all of the things that you've been talking about and thinking about. I know that you've spent time trying to identify better solutions or ways to strengthen and protect these resources so that they don't fail during their time of real need. How would you our current state of these devices in terms of ability to be there when we need them?
Right. That's actually very important because the issue is during hurricane, there is power outage, right? And we need them the most when after a hurricane. And it is important to secure them properly. If I put them on the roof or it is a solar farm, and this is part of what we do. And the best way to understand how they function during high wind is to test them at larger scale to avoid the problems that we realized with Reynolds number and turbulence and all of that. So these are some of the current projects we are currently looking at, how solar panels on the roof would add resilience to existing buildings. I would install this with a new racking system. Perhaps I'm doing reinforcement to the roof by adding this there. And we found something very interesting due to the sheltering effect. Solar panel actually may reduce the loads on on an existing roof, which brings some benefits. Add to that the benefits that we get from the shading. The shading, this would also reduce the AC load, so you reduce heat transfer to the building, so you reduce the amount of electricity you need for air conditioning. So they have a tremendous amount of benefit to be integrated with building, provide energy when we need them, and other benefits. Also, things like micro wind turbine, I believe this is very important because whatever there is a power outage, we have energy close to each home.
Right. So my colleague Bob Fudiker had a couple of comments that wind turbines like oil rigs are built to withstand hurricane force winds. And likewise, they can shut down during high winds and restart after the event. Would those kinds of protocols have protected wind turbines the Louisiana coast during Hurricane Ida, in your opinion?
Well, I haven't looked at that, but yes, as you mentioned, they have to be shot under high wind speed because they are not designed for that. They are not designed for that. So keeping them running at such high speed will bring a tremendous amount of inertia forces that can cause damage to.
What is the biggest surprise that you have found in the research that you've done? You've talked a little bit about some of the unexpected results with solar panels just a few moments ago, creating shade and reducing the structural load on roofs, as well as providing reduced energy use because of that shading. But is there anything else that is truly surprising that caught you off guard that you weren't expecting in the work that you've been doing?
Well, it's simply the Reynolds number. I never thought that Reynolds number would have effects on things like buildings with sharp edges. This is what I have been learning over the years, especially during my PhD. Everybody believed that Reynolds number has minimal effects on low-rise buildings and high-rise buildings. But after that, I just realized it by testing. I realized it by going at higher Reynolds number, we are getting different loads. So it's a surprise. So that was very interesting.
That certainly is. Well, we're coming to the top of the hour, and it's been a really wonderful conversation. And I want to thank you for all the work that you're doing and for all of the contributions that you're making to the future of Louisiana and the world, for that matter, in terms of energy production, the safety of our turbines, and the impact that wind has on our infrastructure. So thank you very much. What an engaging conversation, and we really appreciate everybody's attendance here. Tonight's lucky winner of the WRKF drawing is Peter Diener. WRKF will mail you the NPR beverage tumbler shortly. We look forward to seeing you again on Tuesday, October 26th, for a Science Cafe talk with Dr. Keith Como, Deputy Chief Engineer at the NASA Jet Propulsion Laboratory and LSU alumnus. And he will give us an update on the Mars Perseverance rover mission. Thank you all so much for attending. Thank you for joining us on WRKF's Facebook page. We look forward to seeing you next time. Good night.